Thank you again for the invitation. It's great to be here. I have to do the obligatory warning that all the background sounds that you hear is my dog basically being unhappy that she's not eating what I have currently baking in the oven right now. Anyway, so yeah, I'm going to talk today about TidyModels. There's my contact info. It might be kind of hard to see, but there's slides on GitHub. If you just go to Topepo, T-O-P-E-P-O is my username. You'll find them there. So, I've mostly been, most of the work I've done in R has been focused on modeling. And, what's great, I might not really need to go through this, but, what's great about R is it's always had a really rich set of modeling tools that have been, I think, fairly mature. I mean, they inherited from S. And, I looked at the white book, the S book that was written, I think it was in like 1982. And it's funny that most of the infrastructure we have in terms of syntax from back then is almost identical to what we have now. So if you think about the history of S and R, we've really had this rich modeling environment for quite some time. It's also nice about it has a lot of cutting edge models. So depending on like what your domain is, if you're like a deep learning person, then most of that cutting edge stuff is probably happening in Python. But there's a lot of things around ensembles, trees, regularized regression, things like that, where R is really or R packages are the original implementation of those. And so it's nice to get things sort of as they roll out of the production facility. One other thing is, R doesn't really try to be everything to everybody. So if you have a computation that's not very efficient in R, then you can port that out, and that's always been part of the DNA of R. So there's a lot of modeling methods we have access to through C or C++. In the last like 3 or 4 years, TensorFlow. Now we're doing more with Torch, Stan, Weka. So we have all these things that we can port to R, or at least access from R, which gives it even more power in terms of modeling. But the biggest problem, I think, with R historically has been this consistency problem. There's a lot of heterogeneity in how people write packages. It's not very, CRAN nor anybody else is very prescriptive about the, syntax conventions and things like that, which is great. I mean, we wouldn't have ggplot or dplyr if that were the case. But on the other hand, in terms of modeling, things are very heterogeneous. So there are, like, we've been doing a lot with sparse matrices lately, but the infrastructure around that is very spotty. You can do important things with sparse matrices, but you can't do everything because they're not part of the original sort of implementation of R. So, so sometimes there are like fundamental constraints about what R can and can't do. And then there's things like some modeling package authors not realizing there are a lot of things in R for modeling, like the formula method or factors and things like that. So, sometimes you find this great modeling package, like, ooh, this looks really cool. And then you realize, like, for classification models, you have to do zero-based integers for the classes instead of a factor, which is very un-R-like. And so, so that's been sort of the frustration with using R and S, really. I mean, it was an S plus thing too for so long. I won't belabor this too much, but you've probably seen these examples before. Like, if you want to generate class probabilities from various models, there's a variety of values of the type argument. So it's nice that people recognize that there's a type argument for the type of prediction that you want to make, but otherwise there's no consistency. And then you have, even like at the bottom, you have something where somebody actually is a pretty long time RNS user, just sort of sidestepping the whole S3 object-oriented programming and using just like a function name. So these are the things that are frustrating. And Caret, a long time ago, that was my original impetus for Caret, which was to, make it easier so you don't have to memorize all this stuff, all this minutia. So that's not really a new story. One thing I want to talk about, and I'm going to pick on glmnet a little bit. glmnet's a fantastic model. So it's a model that you can use for linear regression, logistic regression, and a lot of other types of regression models, where you can use what's called regularization methods for estimating parameters. And one of the nice things about that is One of the problems we have in regression is we don't know what term should be in the model. In some ways, you can penalize the coefficients in a glmnet model is something using L1 loss, or what they also call the lasso. And with that type of penalization, you can actually set, or the estimation process can set some coefficients for predictors that are not very relevant to 0. So it's a really powerful model because in the process of fitting the model, it does feature selection. It also has another type of penalty, the ridge regression penalty, which is super helpful. So it's a wonderful model. The implementation is, it's really kind of an interesting numerical problem, and it's not very easy, but the implementation has some things about it that if you've used it, you might be, frustrated by. So I just want to walk through some of the, sometimes within package inconsistencies and use this as an example. So what I want to do is I want to take, show you what the prediction outputs are for various types of glmnet models. Now, one thing about this is the amount of penalization, which is called lambda in glmnet, is a tuning parameter. So like how much you penalize those parameters is based on the value of lambda. So if you have a value near 0 or 0, it's very much like basic linear regression. But if you have a value that's higher, you're driving more coefficients towards 0 and doing more regularization. So that's when you see lambda, that's what that is. And the really, really cool thing about glmnet is you don't have to tell it what lambda should be. So you can get, because of the way the math works out, you can get predictions across any value of lambda of this tuning parameter without having to refit the model. So that's a really important and helpful part of this particular implementation, is that you get all those lambda values for free if you want to tune the model. So, so I'm going to have 3 values of lambda that I'll show when we do predictions here. And what I'm going to start with is, let's say we have like some data we want to predict. We fit like a linear regression model, and we have 2 samples, and there's 4 predictors. It's basic. It has to be a matrix. So if you have a data frame, you have to convert it to a matrix. And if you make predictions on 3 lambda values, using that typical predict syntax, what you get back is you get a matrix. The lambda values are not really encoded into the results anywhere. S0, S1, and S2 are the headers, and those correspond to the smallest, the middle, and the largest lambda values in this particular instance. And so you get this result back that's like, well, okay, I kind of want to know what those lambdas were. So, I know what their values were because I gave it to them. I'll have to merge those in and maybe do some stacking or something with it to get the get this data structure to a format that you want to use. And it also comes back as a matrix. So if you want to do something like ggplot or whatnot, you'd have to convert it to a matrix. And that's fine. Like we can live with that. This is not an insurmountable thing. And so that's like a numeric glmnet prediction. We're thinking like a linear regression model. So now let's say we're doing logistic regression. So now we have an outcome that's like a 2-level factor. We can make predictions for what the class is, or we could get the probabilities back, the class probabilities. So let's say, we have that same X that we're predicting on, but we have some other different models, logistic regression, and we want to get the hard class predictions like A or B. And so what we get now is we also get a matrix back, which is really nice. It's a character matrix. But the problem is when you give glmnet the outcome data, it has to be a 2-level factor. So, you're getting the output back, the predictions back in a format that's really different than what you had to give it. And it's not it's a usable format, but you have to do stuff with it to get it to where you'd like. They probably just wanted to be consistent and make it a matrix, which is fine. Again, it's like 4 or 5 lines of code that probably anybody who's used this model has that will convert this into a more usable format. Now, what happens when we want to make probability predictions? So instead of type equal class, we could use type equal response. That's what glmnet wants. And now what we get is we get a numeric matrix back again. And these are the probabilities at the second factor level. So if we want to get both, we have to do the 1 minus. We also have to restructure this again. And again, it's not that big of a deal, but here's 3 different things we've had to do for the same model under 3 different scenarios. And that's a little bit of a pain. Now, glmnet can also fit multi-level or multi-nomial models. So now let's say we have like the iris data or something, we have something with more than 2 classes. And so what happens then when we want to do this? Well, if we want to get the class probabilities back, we don't even get like a matrix back now. So what we get is a three-dimensional array. Again, the lambdas are not really anywhere to be seen. We're just giving these like placeholder values. And now what we have to do is convert an array to, let's say, a matrix, drop that one dimension down, substitute the lambdas, make it vertical probably, and then do 1 minus the probabilities to get what we want. And so, and again, is this doable? Sure. But now we have like 4 different scenarios. We have 4 different code sets to achieve like predictions in a format that we could just like plot or something like that. And not to criticize glmnet too much, but the feeling I had about this a long time ago, the phrase that like jumped into my mind is, am I working for glmnet or is it working for me? And so, what we want to do is we want to eliminate these issues in R. We want to get things to where they're nice and predictable, and you don't have to do any extra work for any type of predictor, or any particular model should necessitate you from writing specialized code. And so, what we know about like tidy data and things like that, a better structure for any of this stuff might be something where, let's say the predictions are in columns of a data frame, and that the lambda values are not in this weird encoding. You're given the actual lambda values that correspond to what you have. And so, this is an example of maybe what a better situation would be like. So, so how would we do this? Like, what do we need to do? And so one of the things I've been fighting for like a long time is like this retrospective problem where we have, and I last ran this, I should have updated it, but like 5 months ago, there were 16,000 R packages. Let's say like 10% of those are modeling packages, which is probably an underestimate. Now you're looking at many different modeling packages that do different things often. And so the retrospective problem that Kara and TidyModels, part of TidyModels tries to solve is how do we harmonize those without breaking everything? So how can we give you a common interface so you don't have to think about this minutia? But the prospective problem is, and I'll talk about this at the end, is how can we get new R users, or especially people who don't use R or aren't software engineers or anything like that, to make packages that are really consistent with like how R modeling packages tend to work, like using object-oriented programming and predict methods and factors and things like that. And so those are 2 different problems. We'll start with the retrospective problem, and then and then get to the prospective problem of how we can help people without them having to be experts at R. You have probably heard of the Tidyverse, right? So, the Tidyverse is, we opinionated collection of R packages that are designed for data science. They all pretty much work well together, have a very consistent design philosophy and syntax. And so, there are the parts of this that I think are really important. These are the ones that laid out by Hadley in an early sort of publication. Probably the most important one is like design for humans. And that's kind of what I'm getting at is like, you shouldn't need to be an expert in regularized regression in R to be able to use the output of this function, right? So anybody who, who can use R without having to be an expert in certain things should be able to do this stuff. And to me, that falls under this idea of designing for humans. Another example of that would be something where we try to make our function names very consistent and very very useful when you're using autocomplete, right? So in the dials package, we have a lot of ways for making tuning parameter grids. And so those all start with grid underbar. So if you're in the RStudio IDE, you know that to make a grid, I need to use these grid functions. You type in grid underbar tab, and now you have all the opportunities or all the options you have for making grids available to you. So it's things like that that we want to do when we design packages and user interfaces. And so I think most of what I've been doing in TidyModels, I'd say at least like half of it is just making better interfaces for these things. And I love Carrot quite a bit, obviously. I put a lot of it's been like 15 years since I started that, and but it does have a really old interface. And so that's the one thing about it that I want to do better with TidyModels is to have an interface that's more up to date, and I think people will find it more of a pleasure to use. So with TidyModels, what we want to do is we want to at least initially, my design goals for this were, there are a lot of things that are coming out of the machine learning literature, and even like the sort of the statistical learning literature that's been around for 2 or 3 decades, that more classical statistics is not really embraced. And I think part of the reason people haven't embraced it is because there hasn't been implementations for them to do that. So for example, like bootstrap confidence intervals for models are probably better than the standard confidence intervals you get for models. But, people weren't going to like code the bootstrap, 632 method or whatnot to, or the bootstrap T methods by hand. So what we want to do is we want to give better implementations that can allow people to sort of like level up their modeling capability, because now they can do these things. They can, before, maybe 10 years ago, you'd read a paper about things and be like, oh, that would be really cool, but it sounds really complicated. I don't think I can implement that. And so that's part of what we want to do, is we want to enable a lot of new methodology and focus on empirical validation. We also want to build a really reusable infrastructure. So we want, one thing about Caret, for example, is its resampling methods are good for Caret, but their format is not exactly something where you could use them for other things, but they weren't really built to be reusable. And so in the RSample package, which is where we have our resampling methodologies, they basically, anybody who uses a Tidyverse could use those to great effect. And so that's another thing that we want to do. So, and again, we're going to address both the retrospective and the prospective aspect of modeling. So here is the current stable, the current census of like TidyModels packages. I probably have like 1 or 2 that we have sort of in the skunk works that don't have hex stickers yet. We'll focus on a few of these. This one in particular won the Chambers Award. The intern we had last year who did this package won a very prestigious statistical award for programming based on this, which is really nice. And there's really a lot to be proud of, a lot of different contributors, and this list keeps growing. If you want to learn more, if this is all new to you, I think the first place I'd point you would be tidymodels.org. Julie Silge and Allison Hill, who's going to be here next week, spent a lot of time with me and Davis just designing a better website for documentation. So this is really very much geared. We've thought out how the documentation should be handled, and I'm really, really happy with what we got out of tidymodels.org. The get started part is really like, actually has a little bit of a narrative, like, well, here's where you start, and here would be the next step, and then the next step, and the next step. There's a lot of things there for people who are experienced, but if you're just starting, that would be a good place to start. Julie Silge and I are also writing another, well, we've never written a book together, but we're writing another book about TidyModels. You can see it there. I think it's about a half to 3/4 finished. We're going to add basically chapters on some special topics and things that we want to focus on, but the fundamental parts of TidyModels are in there already, and we're adding more as we go. So this would be like the slide to take a screenshot of if you want to learn more. So some things we'll talk about in a little bit. I'll show you examples. Just to highlight a few. Broom is something that David Robinson built, I don't know, quite a bit ago. And one thing it does is it takes standard like R objects, like LM or a t-test object, and it basically puts it into a format that's usable. So like when you get the summary coefficients from LM, everything is encoded as a matrix. The model terms are in row names, and you're like, I just want to make a plot of this. And so Broom is really fantastic at giving you very predictable objects in a format that a more usable format. Recipes is something was like the first thing I did when I was at RStudio. It's kind of like a combination of like model.matrix and like dplyr. It's a really, really, really powerful way to manipulate your data prior to modeling. So it's mostly focused on feature engineering and pre-processing for your predictors. A great example of this, if you do any text processing, is the text recipes package, which has, you can create a whole pipeline for parsing, tokenizing, manipulating text data before, either for putting in a model or not. It's a very nice system for dealing with your data. RSample is something I mentioned before. I'll show you an example of some time series resampling in this with an example I'll go through. Parsnip is sort of like the carrot bits that give you sort of the unified interface to models. And then Tune is a package that sort of like the, these are all like, the Iron Man and Thor movies, like Tune is sort of like the Avengers that sort of like brings it all together and has all this stuff working together. And that's where you can resample models, tune them. It has a lot of different functions that you probably want to have. So we'll go through almost all of these in turn. All right, so there's like a meta package called TidyModels. And I should have used the CRAN versions here. You don't need to have all these. Well, with the exception of recipes, you don't need to have all the devel versions. I forgot to do that before I generate these slides. But it basically loads the core TidyModels packages along with some things like dplyr, ggplot that you're going to want to use anyway. And it gives you a sense of if there are any conflicts with names. The data set I'm going to use is one that we used in I used in my last book on feature engineering. It's basically, we got the ridership of L trains at the Clark and Lake Station in Chicago. And so what we want to do is we want to take the predictors that we have and predict how many people daily are entering the Clark and Lake Station, which is like right downtown. And so the predictors are, I think it's 14-day lags of all the other stations. So if I want to predict ridership at Clark and Lake in 2 weeks, I have all the ridership data from, let's say, today. Those are good predictors. We have things like, as you'll see, date is important, like the day that it is. Things like weather data. I think there's also predictors for whether, the local teams were playing. And also there's another set of predictors in there. Anyway, there's a bunch of predictors that are very useful. You see in a minute. I took a subset of that and put it in the model data package, and that's what we're going to use. So it's called, the data set's called Chicago, and so on. So we'll use that as our predictors. So here's the thing, is like, there's a little bit of terminology, but like, we have columns in the Chicago data. So for example, there's like a date column that's a date object. We have these numeric columns that are ridership values and weather columns and things like that. But like, what are our features? And so the idea of like, this difference between, let's say, features and columns is this whole idea of feature engineering is, how do I take my data that I have, the original like raw data, and encode it in a way that's most easily used by the model. So let's take date. There's a bunch of ways you can represent date numerically, right? So one thing you could do is you could just convert it to an integer, and it will give you back the number of days and some reference value. And maybe your model would work fine on that. Like, it might be nonlinear or a complex relationship, at least you have a number, but your model might have to work extra hard to make that predictor do well in the model. So one thing we could do is we could also represent it by being like factors for like, what day of the week was it, what month. There's a bunch of different ways you can take that data and represent it. And that's the whole idea behind feature engineering. And so what recipes, one thing recipes is really good at is giving you a lot of tools to generate features from your actual columns. Before, you'd have to have like a script that did all this stuff to then get the data in the right format and so on. And so recipes is a method that can do all that in one sort of like. So the initial call here to recipes, you don't have to use the formula method. There's a non-formula method that's more efficient if you have a lot of predictors or a large dimension. But you basically give it the data set, you tell it what the outcome is, and you can say tilde and then whatever the predictors are. And I'm just going to use everything else besides ridership as a predictor. You can have multiple columns, and one thing One thing that's been bothering me since like I've been using S is when you have a multivariate model, you have to like C-bind things together, which is always kind of weird. And so in TidyModels and recipes, if you have multivariate models, you can actually use plus on the left-hand side of the tilde. So if I had like Y1 and Y2, I don't have to C-bind them in the formula. I could say Y1 plus Y2 tilde, like X1 plus X2 and so on. So that's a little feature. So all this does when you start the recipe is it just records what your columns are, their roles, like is it an outcome, is it a predictor, and it looks at their data types, like what's numeric, what's non-numeric, and so on. And then what you can do is you can pipe in new instructions to the recipe, like recipe steps, to tell it what to do and in what order. So one of the first things we could do is we could say, well, we have this date. We probably don't want to treat that as numeric. So what step date will do is take that date column and decompose it into features. Like there'll be a factor for the day of the week. There'll be a numeric for the month number and a numeric for the year. So, we're taking that date column and we're going to make features out of that. Now, day of the week is going to be a factor again, and these two are going to be numeric, and that'll come up in just a minute. In this particular data set, ridership is really low on the weekends and really high during the week. So one of the biggest predictors is day of the week. And so if you have like a linear model, if we just kept it as date, it most likely would not have been able to pick up on the fact that you should have a high coefficient for the weekdays and low coefficients for the weekends. Now, another thing about this data set that we learned before, once we start modeling, is another thing that affects ridership at that particular station is holidays. And so step holiday will also take that date, and you can give it a list of holidays and we'll make indicators for those. So, if nobody's riding the L on Christmas, we can have a Christmas indicator that will then allow it to fit better because it will be accounting for that trend in the data. So, we've made features out of date. We probably don't want to keep it in the model by itself anymore, but we might not want to delete it. So if we get our residual plots and things like that, we probably want to go back and say, oh, what date was this? Instead of figuring it out from all these different features we're making. And so one cool thing we can do in recipes is we can give different columns of your data set different roles. So this would have a role of outcome, and everything else would have a role of predictor, but you can also give columns arbitrary roles. So what I can do is I can update the role of dates to be an ID column that'll help me ID which data point corresponds to what day. And so then TidyModels is smart enough to know that this column should not be added as a predictor into the model. It should still be in the data set, in the data frame that comes out of the recipe, but isn't actually a predictor. And so that's a nice little feature. Now, we know the day of the week is a factor. And so what we can do is, unlike the basic formula method, recipes don't automatically take factor variables and convert them to indicator or dummy variables, as a default. So you have to use actually a step that will create dummy variables. And then, you might notice that we use like dplyr selectors here. And now we have some new selectors that we can show off that are really specific to recipes. So if we wanted to get all the predictors that were non-numeric, like nominal, this selector will capture any and all of them that are in the data set. And I'm pretty sure in this data set, the only one that's there is day of the week. And so we take this factor variable and then make 6 indicator variables out of that 7-level factor there. So we have a bunch of specialized things. You can select things like, give me all the predictors and all the outcomes. You can say, well, give me all the numeric data or the non-numeric. And then you could also filter in the dplyr ones, like starts with or everything and so on. So you can have a series of dplyr selectors like you would with select. Like you might say all predictors, comma, minus this one that I don't want in the data set. You'll see an example of a minute where it uses one of, and so on. So we have a very robust way of specifying which column should be affected by each step. Now, the thing that is a little bit tricky about recipes, users don't have to worry about this so much, but we do have some things like filtering steps where we can get rid of correlated predictors and things like that, but you don't necessarily know when you're writing the recipe what's going to survive that predictor because it's very data driven, right? And so one nice thing is using all predictors or all numeric predictors or something like that, is you can capture the things that you want to capture without actually explicitly saying what columns you're using. So it's very hard sometimes to know like how many principal components you're going to get. It might be 3, it might be 4, depending on the data. And then you can say it starts with PC to capture those. And that's one of the reasons that we have so many selectors for steps, is you might be saying, giving instructions to the recipe to do things with columns that not only do they not exist yet, but you don't even know how many there might be. And so that's a nice little feature. All right, so we've gotten everything to a numeric format that we want to use for glmnet. Glmnet, for example, which we'll use in a minute, doesn't automatically make dummy variables. And so you usually have to do a lot to get your data into a matrix format for glmnet. And the recipe will do a lot more than what like model.net matrix would do, but you can also generate that matrix that you need. Since we're using glmnet, it's a penalized method. So we need to center and scale our predictors. And so step normalize will do that. You can say, take all the numeric predictors, and this will calculate their standard deviations and means and do that normalization. Now, there's a bunch of other things you can do that I'm not really going to do for this data set. I'm going to keep it simple. But one thing you could do is you could do principal component analysis and get back, instead of having the station data, you can get back the principal component scores that represent them. And so the thing about these stations is that they're highly, highly correlated, especially things are on the same line. So if you have like the next station over from Clark and Lake, that's really correlated to Clark and Lake. And having a highly correlated set of numeric predictors can be problematic sometimes. Now, it's not for glmnet, but if we wanted to, we could take those predictors. Stations here would be a character vector of the column names in this data set for the stations. You can select them using one of, and then tell how many components to use. So that's one thing you could do. Another example that's a little more complicated is if you want to use something, let's say like sexier than PCA, which has been around forever. You could use UMAP, which is very similar to t-SNE, if you've seen that from machine learning literature. One other nice thing about UMAP is it can be supervised. So you can tell what the outcome is, and it can make new features out of the data that not only represent a smaller set of features that represent the original data well, but those can also be set up and estimated so that they're correlated with the actual outcome. So we do have some like supervised steps here, and use a different selector to say what the outcome is. Another thing you might want to do is do like a spline. You might find there's nonlinear relationships here. So we have steps for things like B-splines, natural splines, and so on. And the point of showing these other steps is there are quite a large number of step functions for recipes and all the add-on packages that work with recipes. TidyModels.org has a list of all of the steps and all of the models and things like that across all the packages in TidyModels. So if you're looking for something, that would be the best place to go. But there's a lot to do here that can make your model better. So let's take the, what we have up here without any of the extra stuff that I've shown. Let's just fit a model, right? So we're going to basically have the raw station lag data. We're going to have the dummy variables for dates and holidays, and those will be normalized, which is what glmnet needs. And so we'll show how to fit a glmnet model. Now, to do that, we'll use the parsnip package and the functions that are there. And so parsnip operates a little bit differently, where it basically has model types and then what we call engines. And so, for example, linear regression would be a model type. And what that means is the structural equation for that model is something we have a numeric outcome and numeric predictors, and you have slopes and intercepts that represent the outcome. And so that's how we would say that defines like a linear regression model. But then there's the idea that you could fit that linear regression a lot of different ways. So if you could use LM, which is this ordinary least squares, you could use glmnet, which is a regularized regression. You could use STAN to do like a Bayesian estimation of those parameters. There's a bunch of stuff you can do. And so what we do is we have this hierarchy that is, you say structurally what kind of model you want to fit, and that's the model type. And then the engine is either the estimation method or the package that can be used to estimate those parameters in various different ways. And so we'll walk through that in just a second. So with parsnip, what you do is you say what you want to do first before you do it. So if you think about LM, when you type out like LM, Y tilde X and things like that, it's doing a bunch of stuff at the same time. It's doing the model out matrix part. There's even a subset argument that can do filtering of the data. It creates dummy variables for you. It does all this stuff and then estimates the parameters and gives it to you. And with TidyModels, to allow us to do more sophisticated things, what we do is we first say what we want to do, and then we do it later. So me saying linear reg here, the only thing it does is says we're going to fit a model with a numeric outcome and slips and intercepts. And so it's a structural part of the model. And examples of other structural bits would be like nearest neighbors or random forest, or we have time series models and so on. So this says what kind of model you want to use. And there's a function set engine that actually says, well, how should we fit it? Or what package or function should we use to fit it? And when you look at the documentation for linear reg, for example, it gives you a list of all the available engines. And so we want to fit a glmnet model. So, we could fit this using LM, but that's it's actually not a great idea for this data set due to all the correlation that's there. If we have a big data set, we might say, yeah, let's let TensorFlow handle this. So we could let TensorFlow do the estimation, and there's various perks for doing that. You might want to you might have your data in Spark. And so like you can set the engine to be Spark and have it do its thing. You might want to do Bayesian estimation. So let's use Stan for that. But we're going to go with glmnet. And so that's the engine for glmnet. And so that's how we could fit the model. At this point, you might notice that there's no data involved here. We haven't said data equal this or even Y tilde X or anything like that. So all we've said here is we're going to fit a linear model. We're going to use glmnet for the estimation bits. Now we might want to set the penalty. So if we want to do that, we can say, if we know what it should be, we can say, well, it should be 0.1. So let's use that. This mixture is what proportion of lasso and ridge regression you want to do. And so we can specify that in this example, for example, to be a 50-50 mix of those two types of penalties. Now, if you've used glmnet, you might say, well, okay, those are different names. So glmnet uses lambda for this and alpha for this. And so you might say like, well, wait, why are you making me memorize another name? Well, one thing we've done in TidyModels, so we standardize the naming conventions both within and across methodologies. So if you want to use, Keras using like a ridge regression weight decay, that function might have its own different argument for what the penalty should be. So what we've done is we've sort of standardized across different models what the argument should be. So a great example of this is random forest. If you use the random forest package, it's ntrees, I think. But if you use ranger, it's like num.tree and so on. We don't want you to have to remember that. Well, actually, we want you to remember one more, which is trees. But in this case, we rename these things just to make them consistent across models. Another aspect of this is if I'm somebody who's not like I have a PhD in biostatistics, right? But if I'm somebody who's likes this model, but it's just like a data analyst, the jargony nature of some of the arguments is really, I think, problematic. Like if I tell you what lambda and alpha are, that makes sense if you've read the papers for glmnet. But if you haven't, maybe we should use names for these things that are a little more understandable or self-documenting. Like lambda could be anything. It's just like a Greek letter. Now, if you've read all that literature, that's the letter we commonly use for penalties. But why not just call it penalty? And then we don't have to worry about the jargony bits of this stuff. And so that's the reason, those are the two reasons that we rename some of these things. So now we've defined our model. What we can do also, seems like a little bit more work, but there's a lot of payoff in doing this, is we have a preprocessor and feature engineering bit that's in the Chicago recipe object. We have this linear model that we've called linear mod. And the thing is, like when you go to do a bunch of modeling, you might try a bunch of different models or a bunch of different feature engineering ideas. And very quickly, your R session could, wind up with like, 10, 15, or 20 of these objects laying around. And once you find one you like, you might be like, oh, wait, what did I just do? And you might be going through like your art history and up arrowing a lot to make sure you get the right combination of these two things to save, because it's the one that solves the problem. And so one thing we have here, it's not a pipeline because we use pipeline for dplyr sort of and ggplot sort of stringing together. We call them workflows. So in a workflow, basically you add a model to it. You can add a preprocessor that could be just a regular R formula. It could be dplyr selectors like, starts with and so on. And in this case, what we're going to do is we're going to bundle this recipe and this model object together. And then one nice thing about it is you have like one-stop shopping for prediction and fitting. So when I fit my model, it does all the 2 or 3 syntax call you would need to train the recipe and generate the data that gets used in the model. So the fit here actually does 2 or 3 different things you would have to do sort of manually if you didn't bundle these things into a workflow. And then your predict method is really simple. You just give the data. We'll take the first 7 data points of the data, and you get a prediction back. Now, this might look a little bit different than what you might expect. Normally, for like a regression model in like standard R packages, you get a vector back. Well, one thing we do is we in Parsnip want to make a couple guarantees about the data. So, for example, the data that comes out of prediction should always be a data frame. It should be in the order of the data that you gave it. And if you give it 7 rows coming into the prediction function, well, then by God, you ought to get 7 rows back. There are some modeling methods that will eliminate rows if they're missing data. And then you have to figure out, oh, wait, row 2 is not there. How do I fix that in my data? Because it doesn't make a placeholder for that. So when we designed the predict methods, we wanted them to be data frames so you could just, bind call them or cbind them back to the original data. We also wanted to have all the predicted values in columns. So, if you do like logistic regression and you use like GLM, the classes come out as a vector, but then once you have the class probabilities, you might want both of them there. So there are some types of predictions where you get multiple columns. And instead of it sometimes being a data frame and sometimes being a vector, we want it to always be a data frame. Another thing about it is we've standardized the naming. So for regression models, the name of the predicted values are always going to be .pred. If it's a classification model and you predict the class, it'll be .pred _class. So that's always a known thing. You always know the name of things and the structures when you get them back from the predict functions, which is very, very helpful, and so on. So that's if we know, we know our mixture and our penalty value. We could take this, we could, split it into training and test and see how our model did. But this just gives you a basic sense of how workflows and recipes and Parsnip work. Now let's treat it like it's a real problem and admit that we probably want to tune the glmnet model. So we want to find good values of the mixture or the penalty value. We might need to use resampling to do that so we can get good performance estimates. So let's do something a little bit more sophisticated. What you can do in Tune is you can basically tune on it, or in the Tune package, you can basically tune on anything inside the recipe or the model object. So with Caret, for example, there's like a menu, and you can pick off the menu anything you want to tune. But if there's like another argument that gets added to the model, Caret needs to be updated to work with that. And the way we structured Parsnip in the Tune package is anything that is an argument, like a model, like hyperparameter argument, you can tune without us having to do anything new, really. So the way you tune models is you sort of tag them for tuning. So instead of saying penalty is equal to 0.1, what we could do is give it a dummy value, like a placeholder of something called tune. And really all this function does is it returns an expression that says tune. So it's not a numeric value. There's nothing magical about it. It's just something that our code can use to recognize that we're going to try different values for this particular argument to the function, and we're going to be optimizing that. And so we can do that again for the mixture, for the penalty. Like if I'd use a PCA step in my recipe, the number of components in that call would be called numcomp. And so we could say that should be tuned also. And then when we use the methods I'll show you in a minute to tune these models, we can simultaneously tune as many arguments to the model or as many recipe arguments as we want. So like if we had like 3 different splines for 3 different variables, we might want to tune their degrees of freedom. And so we can simultaneously tune all three of those, even though they're in different recipe steps and so on. So it's a very, very flexible and functional way of saying what you want to tune. So let's show you, there's a lot of code on here. The first thing I'll do is I'll create some resampling indices using RSample. This is a time series data set. We don't probably want to just do like 10-fold cross-validation. What we could do is this thing called rolling origin forecasting method, which is a resampling method that basically says, well, let's take some chunk of data at the beginning, use that to fit our model, and then use the next little bit of data to make predictions. And then we maybe on the next iteration of resampling, shift that chunk over by some unit of time. So we have a slightly different data set that we're using to train the model. And then the next little bit gets used for model assessment, like it's our holdout set. So it's sort of like a moving window resampling method. RSample has a couple different ways of doing this. The nicest one is something called slotting period. And what you can say is, my period in this case, we'll say months, because we have data back to like 2001. So it's a fairly large data set. And what we could say is, we want our initial chunk of data to be, since units are months, we want to be 14 years worth of data to fit the model. And then we'll predict the next month as a holdout. And then what we'll do is we'll shift over month by month and do sort of like a rolling month modeling approach. And so when you do that, at least with this particular specification, there's enough data here where you have 19 different resamples of the data, and it goes month by month. So you can see that this number of data points corresponds for those particular years. 14 years ends up being 5,123 data points. This must have been stopping in January because the holdout is 28 data points, which would be February. And then you can see when we bump up, these 28 data points get added to here, and a month gets chopped off, and then March is 31 data points, and so on. So this is how we do the resampling in TidyModels. One nice thing about it is it's a data frame, it's a tibble, right? So if you've used dplyr and you want to write your own way of analyzing the data, you can use per map, mutate, and things like that, known methodologies or known syntax to operate on these particular objects and do what you want. So, one thing about the Tidyverse and TidyModels is we want to create very reusable code. And anybody who's used, dplyr can use this resampling object for their own purposes. So that's really nice. So what we'll do is we'll fit our glmnet model for each one of these resamples. We'll do it across a grid of tuning parameter values, and then each holdout, these would be our holdout data, and then we'll compute, let's say, the root mean squared error and the R squared for each one of these holdouts and average them to get our resampling estimates. And that's what Caret does. It's what MLR does. It's what everybody does for model tuning and grid search using resampling. So it looks a little bit different, but it's the same procedure we would do. So one thing we can also do, like with Caret, is we could do this all in parallel. I'm on a Mac, so I like doMC. We use the for each package. So this will have 20 cores on this machine, 20 virtual cores. So this could split all these computations up across 20 cores and run them. We'll update our workflow. And the reason we'll update it is, or we did update it previously, sorry, to use the version of the model object that has the tune bits in it. And so if we want to do grid search, there's a function called TuneGrid. You give it, the first object is the workflow. TuneGrid figures out, number one, you're fitting a glmnet model. Number two, I know I need to estimate or optimize the penalty parameter and the mixture parameter. In TidyModels, we have objects that handle all of that. So it knows, for example, penalty is generally between 0 and let's say 0.1. That's the range that people usually use. It also knows that we normally analyze penalty on the log 10 scale. And for mixture, it knows it's a numeric tuning parameter that's between 0 and 1. And so knowing that, what you can do is, I'll show you the grid in a minute, but you, like Caret, you can have it generate 25, let's say, tuning parameter combinations of penalty and mixture to evaluate for optimization. So it's very similar how Caret and everything else works. You can give it an individual grid. You can generate your own grid, and we have a lot of functions to do that, or you can just let it do its thing. What this will use is something called a space filling design, and I'll show you what it looks like in a second. But it's a really, really excellent method for coming up with tuning parameter combinations. Caret by default does like a regular grid, which can get very large, and these space filling designs are very efficient and make it really easy to optimize models. And that's what the default is a certain type of a space filling design. So when you run this code, I'd see like my activity monitor on my Mac like light up. It's fitting, let's see, there's 19 different resamples across 25 grids. It's going to evaluate, the product of those two things. I don't do that math on top of my head, and do it in parallel. And it also uses all the computational tricks we use with Caret. There's some things we do with glmnet to make it even faster than it would be. And then once you have this object, there's a bunch of accessor functions. If you just want to see like, hey, rank them by RMSE, the show best function will give you the ones that look best. It'll tell you what the RMSE is. By default, it'll compute R squared and RMSE. So if you want all the values, for example, there's a function called collect metrics. And then you can see for this particular tuning value combination, R squared was about, this is in units of thousands of people. So the RMSE is about 2,000 people for that particular model combination. R squared is about 92%. If we were to print this tune object back, it looks very much like this R sample object with additional columns. We don't want you to have to be per enthusiasts or dplyr enthusiasts. So we have accessor functions or simplification functions for almost everything you want to do. Like if you want to select the best or show the best, we have those. If you want to collect all the metrics and put them in a ggplot, you can do that. You don't have to do any unnesting or per mapping. If you want to get the predictions, there's collect predictions. So there's a lot in the tune package that makes these things very usable. There's also an autoplot method. So let me start on this side first. If I use the autoplot method on this object, it basically gives me some nice visualizations of performance. This is not a regular grid. So what we do is for the row here is for RMSE. You can see as we increase the penalty, performance is pretty much the same. It doesn't really change that much. But once you start to over penalize the model, you're getting rid of predictors that really matter, and the RMSE goes up. You can see on the bottom here, the R squared starts to really drop. You can see the same thing over the mixture value. So you can see it's kind of bad at the very, the ridge model, but like maybe in the interior, like a 50-50 mix actually would work pretty well here. You could do a total lasso model here and get about the same performance. So, this is smart in that it knows that you generated the mixture values between 0 and 1. It knows how to label the axes. It knows that the penalty value is the amount of regularization, so it automatically labels it. It also knows that we usually look at that at a log 10 scale. So if it didn't log 10 these, you would have a bunch of values that were jumbled up on one corner and then a few over here. So it knows how to scale the data and label the data, and it's quite nice in that way. If you wanted to actually see the grid of 25 data points, this is what the space filling design looked like. It's not perfect, but it's designed basically to fill up the parameter space in a way that no 2 points are like right on top of each other. So it does a lot better than like a random grid would do. It fills up the same space that a regular grid would do, but with way less points. And so these designs tend to work pretty well. So I just thought I'd show that. So, what we would do at this point is, if we were happy with the performance of this glmnet model, there's a function that's called select best. And then, you could use that. It just generates a tibble, so you can tell it what lambda and what alpha values to use, penalty and mixture. And then what you would do is there's an updating function that you just give that tibble to along with this model specification, and it actually inserts the penalty value you want to use here, and it inserts the mixture value that we want to use. So then you can fit the final model with the glmnet, the fitted model that you actually want to use on the entire training set, as opposed to the resampled results. And then you could like run that through your test set and so on. So that's what we would normally do. I'm not going to show, that's a little bit tedious. One other thing I wanted to say, I'm not going to show it, is I mentioned the stacks package, which is what our intern Simon Couch did last year, which is an ensembling method. TidyModels is very nice, where if you have a bunch of different tuning results and you want to see, well, would stacking make that model any better? The stacks package, you can just give it a list of, 1 to however many model objects you want to give it, and it will do all the optimizations and feature selection bits to come up with a stacking model that might do better than your individual models. So we have a lot of, I'm not going to go into that, but we have a lot of packages that work in concert with all these objects, mostly because we've standardized how they work and so on. The interface that is very smooth and very easy to use. It does a lot of computations, but the user interface is very nice and very intuitive, even though it's a fairly complicated thing. All right, I'm sure I'm out on time. Everything I've shown you up until now is about like, well, how do we make it easy to use existing packages? So, if you want to, let's say you're happy with your glmnet model or your recipe, but you really want to have good prediction intervals, then you might take the results that you have and run it through, using TidyModels, run it through STAN. So you have a Bayesian model that has, regularization, things like that, that you could then get good prediction intervals and so on with. So, what I've showed you so far solves the idea of how do I go back and forth between different packages to fit different models or the same model? How can I easily do feature selection and things like that, feature engineering with recipes? And so that's all working with existing R packages. Now, the one thing I want to talk about just for a minute is, well, how do we make better R packages? Like, how do we fix this problem where, there's all these different values of type equal prob or response? Like, how do we fix that? And so, so I wanted to show that a little bit. What we wrote is, and it's on a website, it's similar to like have these like tidy data principles and Tidyverse principles, but it's really focused on modeling. And so, I've been doing this for a long time, and I've seen under the hood of most of these models. And I think the thing that I'm convinced makes R modeling a little bit frustrating is it's not very, the people who are writing R packages are really, really focused on their computations, right? So like, let's say you're like doing your dissertation or a postdoc, and you've been thinking about this really cool, like new lasso model that you've been running, and it's really hard to optimize and find the parameters. You've figured out it all, and it's, it's really arcane but it's a good dissertation and a good paper and all that. The thing is, people tend to be, and I'm really no different, so focused on the numerical and technical aspects of modeling that they're not really thinking about the user interface part of modeling packages, right? So I think historically, everybody's been way focused on the minutia of numerics and not the user-facing interface. And so like glmnet's a good example of that. Like glmnet does some really interesting things, but its user interface is not great, right? And it's because I think they just were like so focused on the computational bits. They didn't say like, oh, well, people might want to generate dummy variables. We should let them do that. And so one of the things we want to do is we want to get people to separate those two things, like have really good user interfaces for people. Things like, always making sure that, factor variables where your outcomes are in classification instead of integers or 1-base or 0-base integers or whatever. Like nobody in their like PowerPoint presentation to their boss is going to give like a confusion matrix that has 0 through 5, right? You want to actually have the factor levels in there. And so what we want to do is have better user interfaces. And that means like making sure that we have formula methods, like S3 methods. Let's say, I don't know, just for kicks, let's use type equal prob instead of posterior or response and so on. And then make all of our outputs of that model standardized. A great example of this is Ranger. Ranger is a fantastic package for random forest, but the prediction object you get from predict is a specialized thing that you have to learn what parts of that to extract to get your actual predicted values. Let's not do that. I mean, Ranger can do that, but if we're going to design new packages, we ought to give people results back that are reusable and standardized and predictable. And so the thing about that is I've been doing this for a long time, and I recognize that if you are like doing your dissertation or your postdoc and your advisor says, hey, write an R package for this at the last minute, what you don't want to do is have to spend months figuring out like, how do I write good R code, or how do people do modeling, or what does S3 mean? So what we did is we created something called the hard hat package. And if you've seen the use this package, it's very similar to that. What it does is you have like an R session open with your modeling function. And I was working on Torch for let's say just like a simple neural net. So the package is called Lantern. It's not on CRAN yet. And so I had this function called Lantern MLP. This is the neural net bits. There's like a Lantern LM and things like that. And so what I can do is I can write all the computational bits that I care about. That I have this fit function that takes X and Y, and they have to be matrices, and all the really specific encoding bits and all the things about the actual model fitting. And then what I can do is I can say, create modeling package, point it to some directory, tell what the name of the model should be, and does all the scaffolding. So it sets up the package, it sets up, any dependencies. It takes your function, puts them in a directory, in the R directory. It sets up the predict methods. And it does, there's still things you have to do. You have to say, well, this is a regression model or classification model, and then connect your implementation to the front end bits. But it does all the front end bits for you. So for example, it'll always take a formula, a data frame, or a matrix. So if your underlying model always needs a matrix, it handles all the bits that get it to a matrix, right? So you don't have to worry about, it also has a recipe method. So if you want to have various types of inputs into your model, you now don't have to learn how recipes works or model.matrix works or all that stuff. Hard Hat will just lay that out for you, and then you just connect your bits to that. And now you have a modeling package where you've done like 10% of the work to get there. 2 years ago, I was in Madrid for our conference. Here's like a demo where I took like a really simple model and just during like a live coding keynote, took 9 steps using Hard Hat to get it all working and compiling and everything. So that's a good place to start. And what we want to do is we want to tell people as much as possible about Hard Hat, because if I had this when I was like writing R packages or when I was doing my dissertation, this would have been the best thing in the world. I don't have to care about all that other stuff. I can just worry about the parts that matter the most to me and let, Max or Davis actually wrote this, let the RStudio people, whoever, lay out all the tracks for my train to run on. So that's very nice. And hopefully as time goes on, this will solve some of the issues regarding the inconsistencies in modeling package. At least that's the goal. So again, first part of the presentation was about the retrospective bits. This is the prospective parts, and that's pretty much it. Big thanks to everybody at RStudio who contributed to TidyModels, especially Davis and Julia, Allison. Desiree did great work before she was at RStudio on making our website really usable and helpful. And thanks for the invitation to speak.
All right, thanks very much, Max, for that great talk. Let's open up for questions. Please feel free to jump in with your questions. I know no one wants to hear my question, so I'll ask a really bad one to motivate people to have better questions. So the thing that stuck out to me was, why do you put the dots in front of the column names, the result from the predict object?
Yeah,
That struck me as strange.
Believe it or not, there are people who have predictors that are called pred, right? So then if you bind things together, then you don't have it doesn't try to merge on that value. So it's mostly to keep things Yeah, now it's possible somebody's gonna have a dot pred, right? So now we have to like double dot. We're not gonna do that, but like that's our first shot at avoiding naming conflicts in tuples.
Great. Yeah, good. You thought of everything. That's great.
Well, yeah, we weren't the first people to think about that.
Yeah.
But, it's usually part of the presentation where I make sure people are still here because somebody's asking questions.
Yeah, I'm here. I've actually been trying to follow along with your demo in RStudio, and I'm getting this error that could not find functional nominal predictors, and it's
right. That is in the develop version recipes. So you have to load from GitHub. You have to do yeah. Sorry, I should have mentioned that. And this is an important piece. Like Mine, who a lot of you probably know or heard of, has been teaching a lot with TidyModels. And up until recently, all we had was like all predictors are all numeric. And we had a bunch of people who, like, if let's say you have a classification outcome, right? So ridership here is a number, but let's say it was a class, and people were just doing step dummy all nominal. And what it was doing is converting their outcome to a binary indicator, right? Now it's not a factor. And then they're like, wait, where'd my data go, right? So once we thought about it, Mine observed this and said, is there any situation where you would really do all nominal and not like, and so I think like 99% of the time, people want to run these functions on just their predictors. And so that's why we made this new, and I was using it because we want to move all of our training materials to this instead of this. Yeah, the reason is you need to install that.
Well, thanks. Is there any particular, I mean, I guess, it's a style thing, but like having all-star predictors versus like using the existing all nominal, all numeric, and an argument to that's like predictors are all.
Yeah. Naming things is really hard. And
oh, yeah.
Yeah. I think that most of the time I spend when I present at our Tidyverse meeting is like, please look at my API and tell me the parts of it that suck, right? So like we've been having a lot of debates about like good and bad names for things. So hopefully this stuff, nominal, I thought people would, was not smart of me, but I thought people would pick up on that means either string or factor. So we might make like all categorical or something like that. Or all non-numeric is not a good idea. But like we might refine these better. We won't get rid of selectors, but once we get feedback from people, we realize that okay, maybe naming it this way is not great, or maybe having this combination of them is better. Was there another question?
Yeah, I've got a question. Oh, sorry. I've got a question real quick. But you talked about the grid, I guess selecting hyperparameters using grid. Is there any way? I mean, I've used DE-Optim to do a hyperparameter selection, basically an evolutionary optimization routine. Is there any provision for that in this?
So not that method in particular, but we do have the one that's very in vogue last couple of years is Bayesian optimization. So so we have that. We also have simulated annealing. There's a side package called Fine-Tune that has simulated annealing. There's also a class of methods that have been around for a long time, and they're great, and I just want to promote them more. It's something called racing methods, where it's like a grid search, but you don't have to do the full set of models. It's like a very adaptive grid search that will resample ones that seem like they're doing well and discard ones that aren't. So if you have like 10-fold resampling, after like 3-fold, you might realize, oh, well, this penalty value is never going to win. So why am I bothering with that? So we do have some adaptive methods. Yeah, I mean, we'll add them as time goes on. I'm not even convinced like the iterative methods, like we have simulated annealing and Bayesian optimization right now. There's a tons of different ways we can do that. I'm not sure that we're going to get much of a bang out of having more. So I kind of have to be like really convinced that like, you know, people can do their own package, right? So I mean, they can do that, and we definitely want to help people do that. But in terms of stuff we're supporting, I think the 2 iterative methods we have now pretty much cover what we would need. But prove me wrong if I'm, you know, tell me I'm wrong.
Question.
Yes.
Can a current version of TidyModels handle process variables combined with mixture variables?
So you're doing like mixture designs, like DOE?
That is correct.
Yeah. Yeah, if I remember right, you would just need a different way of writing down the model. So we don't have anything automated to do that. But let's say you just had like mixture values, depending on your design, like, you know, that mixture process would be like either all main effects or just 2-way interactions and things like that. So you would have to specify that format using either a recipe or probably just a regular formula would work well for that. We don't have anything canned to do that, but it should be able to do that just fine. Yeah.
Does the TidyModels handle desirability function?
No, not yet. I like, the thing is, you put me on public transportation, like if I go to, like, I'm in Connecticut, if I go to the New York meetup, I will write an R package on the way down. And I did write, like, I have a desirability package. It's not very tidy, so I've been trying to write a successor to that, but it's not the highest priority. So the desirability package still works really well. So as an example, like, let's say, you know, I want to optimize my model on both RMSE and R squared, right? I can do collect metrics and use that with the desirability package to find the most desirable tuning parameters. So it's not built in, and I think I even have like a GitHub issue for this. It's not built into the system right now, but it's totally doable if you want.
Yeah. Okay, thank you.
No problem.
So there's a question in the chat from Ken. So he was asking for parallel computation with TidyModels, is there any preference for do parallel, do MC, or another framework?
This is a weirdly like controversial thing. I've used do MC. So, okay, the first answer to that question is, if you're on Windows, basically your options do parallel. So you can't run multi-core on Windows. So if you're on Windows, that's the kind of like the end of the discussion. There are other things you can do, but between those two, you would have to use do parallel. Multi-core for me is reliably the best thing ever. I think it's easier to use than like a PSOC cluster. I find it to be more reliable. Now, the person I think in the R community right now, the gentleman who developed 4H died a year or 2 ago, and the person besides him who knows the most about parallel processing is Heinrich, who wrote Future. And if you actually use the Future package with multi-core in the RStudio IDE, it won't let you, because he's found it to be unstable. I've never experienced that, but I trust him enough to know that like he feels really good about that. So my personal favorite is doMC if I'm on Unix or a Mac. Heinrich, I think, disagrees with that. So, you know, there's not really much of a performance difference. So for me, it's more of like a reliability and usability issue. But there is almost, I've done simulations and benchmarking on this for like the last God knows how many years, and I've yet to find like a real difference when things are working fine between PSOC and multi-core.
Hey, Max, great talk. Thank you. Can I ask you 3 quick questions? The first is, I guess I was a big fan of Carrot a while ago, and I actually gave a Carrot workshop like 2 months before people started talking about TidyModels. Yeah, so I was just curious if you did like have any code reuse from the Carrot package.
Code reviews from the Carrot package.
Reuse.
Oh, code reuse. You mean like, are we using bits of caret inside TidyModels?
Yeah.
No, not really. We do have some things like an R sample, like if you can take your control object and convert it to an R sample object. I don't know that we reuse any code. Like I
Okay.
basically,
I was just curious.
yeah, I basically started fresh. Like there's a lot that I learned from caret and I'm really happy about it, but under the hood is kind of a mess. It's like somebody who was writing an R package in their spare time, and then their boss said, yeah, don't work on this anymore, and then had to support it once 200,000 people a month were downloading it. There's things inside of caret I'm not proud of. I mean, they work, but it's kind of a mess. And so it's not really well built for reuse.
Without the hard hat package, right?
Yeah.
Last time I checked, there was not a place where I could see like the default parameter or hyperparameter for certain model, for certain engine. I was wondering if there's one now.
So I think maybe a version or two ago in Parsnip, I think it's like at the bottom, we have like an engine argument. Let me open it up. Here, let me open an RStudio window and share again. So let's say I do like pick a model.
SVM.
I do SVM, RBF. Down towards the bottom, we have like a little table that tells you. So like if you're like, so we use cost, KernLab uses C, and Liquid SVM uses lambdas. And then when there's a default, we put it in here.
Gotcha. Thank you.
Now, one thing we're going to do is probably, maybe not in the next month or two, but for some R packages that David's built and another one I can't think of within RStudio, we're gonna reorganize all this model documentation because it can be like overwhelming. There's like a lot here, and so we have some really good ideas about how to reorganize all this. There's a lot of information here, and some of it's kind of important, and so so this will look different like in 6 months, and I think it'll be a big improvement on readability.
Yeah, I think that'd be really helpful. Yeah, I have one last question about unsupervised methods, but
yeah, go ahead.
Yeah, so I know that there's k-means, but yeah, what direction are you thinking in terms of more unsupervised models and such?
So some of that depends on what you want to do with them, right? So let's say you're doing like dimension reduction and supervised stuff. Like back when I was in drug discovery, we were analyzing like 5 or 6, maybe like in a 1 week period, you have like 1 or 2 RNA profiling experiments, right? And so we spent a lot of time figuring out good ways of doing dimension reduction to look for outliers in the experiment, things like that. So if you just want to do that, like plot the dimension reduction, things like that, then recipes is really good at that. Like recipes can be used on their own for all sorts of things. For clustering recipes, we'll probably add clustering steps, but it's not really like what you would do with a clustering routine, right? So like you're not like really generating features usually using clustering. So we do, in fact, we've talked about having a tidy API for clustering. So Kelly Bowen, I can't remember how to pronounce your last name. We met with her about 2 weeks ago and just brainstormed a bunch of syntax. And we kind of have 2 big things in TidyModels we're doing in the next like 6 months, but that would be one that would bump up in priority. And it would be a little bit like caret, like how can we provide an efficient and unified interface to all these different clustering methods? And between that and Broom Tidy, can we have better plotting methods, and so on. So we want to do things like that. We want to make sure that the syntax fits the usage. So like including it in recipes, it's not really all that satisfying because that's not how you would use it. So yeah, we're doing these things. I'd say if you want to contribute to that or want to be involved in discussion, I would like tweet at Kelly. And then we have like a planning repo where we put our thoughts down about different stuff. So it's TidyModels like /planning. And so I think the idea is we're going to put up a README there that just brainstorms like, you know, for example, like if we have like a clustering function that does the actual clustering, should it take like the distance matrix or should it take the raw data? Right, or both, like, or either, right? Because like if you know you're going to be using, thank you, if you know you're going to be using Euclidean distance, you shouldn't have to recompute that a bunch of times, right? So the things like that we want to think up, like how would we interface those things? That's really where it's at. And then the doing of it is probably not going to take a terrible amount of time. We just want to we spend a lot. Historically, I've not thought about the interface until I'm done writing the code, right? Which is a horrible idea. So we spend a lot more time thinking like, all right, well, if I were writing some code in an R Markdown file, like doing actual data analysis, what do I want it to look like? That's what we do with stacks. Like we look at the stacks package, we're like, what would we like our code to look like? And then we developed all the stuff to fit that. So that's what we're going to do with this. Yeah.
Yeah, that makes a lot of sense. And I agree that planning is it's very, very important. So yeah, thanks.
There's a question a few back in the chat about checking for collinearity and things like that and robustness and just checking your model sanity checks. Is there a way to do that with TidyModels easily?
Yeah, so we have like augment methods. So some of those things you would do would be based on the type of model you're fitting. So like the hat values and things like that would be the first thing I would do for collinearity. Hat values are really specific to like linear models, like slopes, intercepts. So like if you're fitting a random forest model, that can help you diagnose things, but it's not part of like a random forest. So we do have a model called applicable, which you can use to compute hat values. What applicable does is it's based on this idea of like applicability domains, in that back when I was working in computational chemistry, we were building tons of models. And what we were always really afraid of was to be somebody making a prediction on a data point that it was unlike everything that went into the model. And so applicability domain basically tries to measure how similar your data were to the original training set. And one way to do that is with hat values. So we have a nice interface, for example, to hat values through applicable. Other types of model checks, it's not announced yet, but one thing we want to do is have a summer intern this year that does like a Shiny Models package, like Shiny Stan or something. Like you give it your TidyModels object and you get a bunch of different diagnostic, like plotly graphs, right? So like in that Chicago data, there were like 2 or 3 data points we could never predict well. And it turns out one of them was like a day where there was Millennium Park had like an art fair, Lincoln Park had a free concert, and there was a parade for the Blackhawks who had won the Stanley Cup, right? And the Blackhawks are never going to win the Stanley Cup again. So like, you know, you can't make an indicator for that. And so, but it took us a long time to figure that out. And the idea would be in like the Shiny package to give it your model object, see those plots and be like, all right, who is that? Like what happened there? And be able to figure this stuff out. And so having similar diagnostics would be, I think, part of that. Yeah.
All right, great. Thanks for answering all those questions. I think we should stop it there. It's getting kind of late. So thank you again, Max. That was a great presentation. I've learned a lot. Thank everyone for attending and all the great questions, and hope to see people at the next one.